Today I'm going to try to quickly explain how the electrons fill in, and that gives us the properties that are known in the families of the periodic table. So I'm just going to try to go through this real quick and sort of lay a basic understanding of this down. So as we move down the periodic table, more and more orbitals are available. So on the first row of the periodic table, there's only one set of orbitals that has one orbital in it, and then the next two rows adds 4 sets of orbitals each that will hold 8 more electrons. So we have the row totals. First row, 1 orbital. We have 2 electrons available. Second row, there's 5 orbitals total, 4 here, 1 up here, so we have 10. So the goal for an atom, if an atom actually has a goal, is to get all of their electron slots full. So if you have 10 slots, this set of orbitals is full, the electrons are going to try to fill in this next set of 8 orbitals. And they do a good job of that through the first 3 rows. And then things kind of get confusing here, and we'll talk about that in just a second. So as we go down, the orbital configuration, the number of orbitals and where they're located and how they fill, it makes sense to begin with. We have the lowest energy level with 2 electrons, and then we have another energy level, another set of orbitals. So in this period, or this row, the electrons are going to fill, so there'll be 1. So there'll be 2 in the first, and then the 3rd, the 4th, 5th, 6th, 7th, 8th, 9th, and then the 10th electron. As we get down here, when the next group of orbitals become available, the order of filling those orbitals slightly changes, and if you will, the set of 8 becomes at the back row. I use a movie theater analogy to say that there's a strange movie theater that after the first 2 people show, the owner always puts 8 slots on the back row for some reason. So as we're going along, the last back row is always filling until we get into here. So I'm going to show you an interactive periodic table and talk a little bit about what it shows us about electron configuration. All right. So we're looking at an interactive periodic table, and as we roll the mouse over the different elements, in this spot here, it shows where each of the electrons is. So if we look at hydrogen, we see that there's 1 electron, and it's on this first period set of period orbitals. When we go to the helium, we see that the second slot has been filled. And then as we move down, now we see on lithium that there's, I guess we'll look at beryllium, there's 2 and 2. So the lowest energy level orbital has its 2 electrons, and then the next set of orbitals has 2 electrons as well. As we go over to the other ones, we can see now on fluorine, here in this window, you'll see that the first set of orbitals has 2, and the next set has 7. And I'll put a link to this periodic table in the comments on the overscreen, so you can find this and play with it yourself. And as we go down this column, we see that the 8 now is full because neon has its both sets of orbitals full. Chlorine is almost done. It has the first set full, the second set full, and the third set is missing 1. So naturally, if we slide over to argon will be full. So we can look at any element and see where the electrons are located. Now, as I said earlier, periods or groups 2, 13, 14, 15, 16, 17, and 18, they're all very predictable. So if I go down column 13, you're going to see that on the last row, there's always going to be a 3. So if I go down column 13, so there's a 3, 3 on the back, 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 all the way down. Same is going to be true for columns 1 and 2. There's always going to be 1 on the back row. And so you can see that as I go all the way down, the back row always has one extra electron on it. It's also true for column 2. It's true for all of these columns. But in the middle, this is the transition area. The predictability is not the same. So here we have 2 on the back and 9 on the row before, and then we have 10 on the row before and then 2, and then it jumps around. So I have 13 and 1, and if I go down the column, I still have 1 on the back row, but then the next row down I have 2 on the back row, and so on. So the pattern does not work in these middle elements because there's 2 sets of orbitals that are filling up at the same time. We can follow the pattern through columns 1 and 2, and then 13, 14, 15, 16, 17, 18. The pattern is very, very consistent. So I think this gives us a really good way of experimenting and playing around this periodic table at ptable.org. And we can kind of see what the electrons are doing. I think it's real helpful this way. So these columns are very predictable, so we can always know that every row in column 1 has 1 electron on the back. Every row in column 2 has 2 electrons. And I say on the back, what I mean is it's filling a set of orbitals, and that last set of orbitals has 2 in it. 13, 14, 15, 7, all these guys are all the same. So the gist of it is, as we go along, we can always know that in columns 1, 2, 13, 14, 15, 16, and 17, there is an opening for or an excess of electrons that's predictable. So in column 1, there's always 1 excess electron. Column 2, there's always 2 excess electrons. So they'll be happy to give them up because we're trying to get to 8. Columns 13 has the 3 extra. Now column 14 has 4. So it'll give them up or take 4. And though there's variances in this because it's chemistry, there's always lots of variances. And then 15, 16, and 17, they're trying to fill their orbital with electrons. And so we say that column 15 is looking for 3, column 16 is looking to take 2, column 17 is looking to take 1, and column 18 is happy. It doesn't want to give any up, it doesn't want to take any more because all the orbitals are full in column 18. When I was reviewing the clips from yesterday, it ends up sounding like I'm saying that all of the elements want to grab other electrons from the atoms till they have 8, and that's not exactly accurate. While these guys are trying to complete their orbitals, while the elements in columns 15, 16, 17 are trying to complete their orbitals, the other side of the periodic table, they're trying to complete their orbitals, or they're trying to get to the point that they have a complete orbital, and the easiest way for them to do that is to give up the extra electrons that have filled into the next set of orbitals. And so what will happen is the elements on this side will bond with elements on this side, and together the net charge of the molecule will still be 0 because the number of protons and neutrons are the same. And one way to think of it is that the electrons from this side hang out with the electrons on this side, so the orbitals are full, and this side has a clean outer orbital that's also full, but for the whole molecule, the number of protons and neutrons stay the same. So I wanted to clear that up so it doesn't sound like I'm saying that these guys are trying to find 7 electrons in order to complete their orbital. For them, it's just easier to give away their 1 extra and get their outer set full. These guys, it's easier to find 1 electron, and that's why we see elements on this side commonly bonding with elements on this side. So you'll see the sodium chloride. But as a general rule, it's easy to think of it in terms of 1, 2, 13, and 14 giving up electrons, and 14, 15, 16, and 17 taking in electrons, and of course column 18, they're just happy the way they are. So I wanted to add this to the end of the video. I already edited it and rendered it and everything, and I watched it and previewed it before I loaded it up. I wanted to add this comment in just to kind of clear things up. So hopefully this will be helpful in understanding a little bit about how the periodic table is organized by groups and families. and a little bit about how the elements are going to interact with each other. So I hope you enjoyed the video and keep watching. Thanks.